So today we're very happy to have Dr. Reza Najafi with us. He's an associate professor, as you can read here on the screen, in civil and environmental engineering at Western University, not so far from here. And he leads there the HydroClimate Extremes and Climate Change Lab. Drawing on expertise in engineering, hydrology, climate science, risk assessment, and data analytics, his work explores the dynamic interactions between natural hazards and infrastructure systems. His work is highly interdisciplinary. That's also why we're very happy to have him here with us today, and addresses the growing challenges posed by non-stationary hydroclimatic extremes, particularly floods and droughts. Dr. Najafi is the co-founder and co-director of the Center for Multihazard Risk and Resilience at Western University, which fosters cross-faculty collaboration and practitioner engagement through research training and annual workshops. He serves as associate editor for Water Resources Research and the journal Weather and Climate Extremes, and he contributes to national climate assessments and resilience frameworks supporting both the natural and built environment. Today he's going to talk about the implications of compound flood and drought hazards for risk and resilience, and please join me in welcoming him to the floor. Thank you so much.
Thank you. All right, good morning everyone. I hope you're all doing well. First of all, I would like to thank Roy, Julie, and the Water Institute for their invitation. It's a great pleasure to be here among you. So today I'm going to talk about extreme events, and hopefully I will show you that many of these extremes are not happening in isolation. They are interrelated. But before I start, I was thinking about how to start this talk. I remembered a few days ago, I was talking to a friend, and he said, well, I want to hire a snow removal service to take care of the snow shoveling in the winter, but last time I did it, it wasn't quite a good experience. It didn't snow that much. I remember that it was a couple of years ago. We had a strong El Nino effect, warm winter, not so much snow. This year, though, we have a weak La Nina and a negative PDO. So that signals, based on our past understanding, that that's potentially leading to more snowfall, more lake effects, so not a too bad idea to hire a snow removal company. So that gives us power. That information gives us knowledge at the individual level for decision making, but also that's very important for agencies, from municipalities, river forecast centers, to provincial government agencies. So suppose that you're planning for your area, you know that there is heavy snow, global warming, so fluctuations in temperature, there might be a risk of rain and snow event type of floods. Or you might have a large spring freshet, so on and so forth. So this information is valuable. Thousands of years ago, our ancestors, they had some understanding of the weather, but not to this depth. However, that understanding helped them form civilization. Looking back thousands of years ago, like 6,000, 7,000 BC in Egypt, close to the Nile River, one of the longest rivers globally, civilizations formed, not just because of access to fresh water, but also because of its predictability of the regularity of flood events, sometime between July and November. That flood was not disastrous for them. It was actually quite fruitful. It helped them nourish their farmlands and develop food and grow. So one would say reasonably that without that predictability, they couldn't flourish. They couldn't build these monumental structures. And much worse, we wouldn't have movies like The Mummy. Now, flash forward a few thousand years, couple of thousand years in dry lands of Persia. There was a big empire, so they had to grow, but access to water was quite important. Well, they didn't have that huge amount of fresh water on the surface, but the ingenious idea was to use the groundwater through the horizontal tunnels called canals. And in the middle of the desert, they could develop civilization and grow their land. It was sustainable because during drought, they didn't have a lot of evaporation issues. And also during dry periods, they could still use the water from groundwater. A couple of hundreds of years later, Romans, they built aqueducts to transfer water from wet regions to dry regions, and that helped them to grow as well. So good or bad, did it increase their vulnerabilities? That's not of our concern, but the point is that this understanding of the climate system is important to grow, to make civilization. And his story shows us that fluctuations and deviations from these regularities have led to significant socioeconomic impact, such as Egypt, a mega drought that led to lower than expected floods, so less food, famine, and lots of related problems that ultimately led to the collapse of the Old Kingdom. Or in Persia, where the Sassanid Empire, very extensive land, they managed, but during the floods of the Tigris, many of the canals, their systems, their agricultural lands were affected. So that could be one of the reasons that they collapsed 5 years later in a war. And the Romans as well, that were affected by fluctuations between floods and droughts. So these are important. They can have, as we see nowadays, they can have very critical socioeconomic impact. And what we notice nowadays is that these extremes are becoming as if they are always in the news. They are becoming more and more frequent and more intense. I'm sure you've heard of the Hurricane Melissa a couple of weeks ago. So we know that the climate is warming. That's what we have observed, and that's what the models show. In the future, we expect global warming, increases in temperature, and that has consequences. It can intensify hazards. And I saw this graph from individuals in NASA. It's not a drastically long record, but it gives us an idea of how sharp we are experiencing increases in these kinds of floods and droughts events. They combine the land areas and also the intensity. So that's a warning for us. Why do we see these disasters keep intensifying? There are many reasons. We have population growth, urbanization. People want to have access to resources, so that increases the exposure, especially with growing infrastructure. Our infrastructure is aging, right? So majority of the dams in Canada are 50-year-old and beyond. So that means that they are more susceptible to extremes. There is the climate change impacts, warmer temperatures, and related increases in extremes like heat waves, wildfires, droughts, and so on and so forth. So in this talk, I will touch on those through the context of compounding and cascading events. I want to show that many of these events and the corresponding consequences are interrelated, and they exacerbate each other's effects. So this graph kind of summarizes all of these. On the top, you see the hazards. We have floods, tsunamis, earthquakes, droughts, heat waves, etc. But when we see an event, there is a sequence to those events. Like when there is a drought period, usually there are multiple heat waves occurring as well. And these dry conditions and heat waves, they generally lead to extensive wildfires, like what we experience in Alberta. Or during hurricanes, there are intense rainfall, but also extreme wind events, right? Or we have a thunderstorm, there's hail, tornado, heavy rainfall. All of these, they interact and they cause problems. But when we get to the infrastructure, our infrastructure system is also quite interrelated. The key infrastructure, including the roads, transportation systems, the electricity, so on, healthcare, etc. These are all also quite interrelated. Imagine you're sitting in a city, there is extensive heat wave, the AC is on, so far so good. But because of that heat wave, a wildfire has occurred 100 kilometers from where you live. Now, the power lines are down. So the AC is off. What do? You need to move to some other places, especially it's important for elderly. But what if the transportation system is down? So that means that in infrastructure risk assessment, this domino effect of the failure is quite important. And there are many studies that show this. So in today's talk, I want to mostly focus on these types of hazards, water-related hazards, mainly floods and droughts, that are interacting with each other, and also touch a bit on the cascading infrastructure failure. The figure on your left shows a wildfire in Los Angeles. It was big news. It was a very severe wildfire event last year. And one thing that interested me was the fact that the region was relatively wet for 2 years. And the above normal rain led to the exacerbation of this flood, how it expanded and grew vegetation and shrubs in the land. And those shrubs, when the wet period quickly turned into a dry period, they became fuel for these types of wildfires. So that was a quick shift from a wet period to a dry period, exacerbating the flooding, the wildfire. On the right figure, you see the BC flooding in 2021. There was a heat wave, and then subsequently extreme wildfire in something around June and July. But just a few months later, 3-4 months later in November, they had an atmospheric river type of intense rainfall for 2 days, and that the same areas that were affected by wildfire were also affected by flooding. So these are the events that are called hydroclimatic whiplash. Sometimes you call it hydroclimatic swings or transitions that show us such events are becoming more and more common. What's the problem with that? Some of the issues with droughts and wildfire is that the soil becomes so-called hydrophobic. Traditionally, in our hydrologic simulations, we consider dry soil as a type of soil that absorbs more water. But when it becomes hydrophobic due to extensive drought, it actually repels water. So during heavy rainfall, it doesn't get absorbed. It quickly turns into runoff and exacerbates flash floods. On the other hand, when you have floods, there is erosion. And with erosion, there is less infiltration. There is less groundwater recharge. Reservoir management and overall water management also becomes quite critical because you simply cannot manage the water levels in the reservoir because of these sudden changes. And knowing that in a warmer climate, the atmosphere acts like a sponge, and the sponge gets bigger and bigger. So during drought conditions, it absorbs more moisture from the soil and from the surface water. And during rainy days, it dumps extensive rainfall that causes flooding. So these events are expected to intensify in the future climate. Our historical data kind of confirms that these kind of events globally has shown up, like in Cairo, Egypt. We see a drastic shift, sudden shift from wet periods to dry periods. In Lahore, we see the reverse. Interestingly, I saw another image for Tehran, which showed a shift from dryness to wetness, but it was published a couple of years ago. But now, after a couple of years, the city is experiencing severe droughts, in fact. And we have regions that experience these whiplash events, sudden shifts from extreme wet to extreme droughts. So, considering climate change effects, we cannot use understanding historical norms for our future planning. What happens in the past do not necessarily happen in the future, and in the future, we will experience events that we never experienced in the past. So we should rely on the models. We have the general circulation models. If you want to do more high-res simulations. We use the regional climate models. And these are the models that are being much more advanced nowadays. So some of our results are based on those. Some of those are based on outputs of these models that are used to drive land surface modeling. So using these models, we can have an understanding of future changes in these events. This is North America. We are looking at scenarios from 1.5 degree global warming to 4 degrees global warming. And these show the intensities of hydroclimatic whiplash in different regions. So reddish areas are the areas that are experiencing or expected to experience more intense hydroclimatic whiplash. And to me, the signal is quite strong. First of all, areas that have already experienced these events, like in California, Texas, BC, these are the ones that are also expected to continue experiencing these events, but at a very stronger rate. But also there are areas close to the Atlantic, Northeast, and Southeast. And in fact, if we take all of these regions and we divide them for different time slices, depending on the global warming levels, for both transitions from dryness to wetness and wetness to dryness, we see very contrasting results. So each color shows a specific period. And we are going from green, which is our current baseline period, down to light green to the 4 degree level. And all of these are showing a trend toward higher intensity and lower transition time. What is the transition time? The time it takes going from one extreme to the opposite extreme. So that's alarming. That's problematic because we're used to having some normal times in between to get adjusted to the future droughts or floods. Now, the West Coast seems to be a hotspot for these kind of weather events. So we looked at it as a case study, looking at both the stream flow variations, indices based on just precipitation, and indices based on precipitation and evapotranspiration, which is reflected in SPEI. And looking at both of these, going from the base period to 1.5 degree global warming to 3-4 degrees, this is based on only the precipitation or water availability. This one also includes the energy of the system as well. And so that's the area of the West, including the BC and Oregon, those regions. And as we move to a warmer climate, we see more and more of these events occurring because of precipitation fluctuations. And when we bring the energy of the system into account as well, northern areas become more susceptible too, because as you know, now we have snow regime as well, and it's a clear signal showing more frequent weather whiplash. Now this will be reflected in the stream flow. So these are the gauges, stream flow gauges that we investigated. All of these simulations are based on land surface modeling, and they show we go from a kind of somehow relatively rare events to much more frequent events of transitions from flooding to drought. So basically experiencing maybe sudden spring freshet or successive rainfall events to a hot, warm weather in the summer and a dry condition. In 2017, there was an interesting incident, not quite interesting, unfortunate, but in the scientific sense, there was the Oroville Dam failure. So California experienced multiple years of drought. And after about 2015-16, the drought ended with intense rainfall. That intense rainfall and that abrupt change from the dry period to the wet period caused issues. One of them was this failure. So the reservoir level increased quickly to the extent that they had to use the emergency gates and use the spillway. So there was a hole that generated in the spillway, and they had to evacuate close to 200,000 people downstream. Now, looking at that particular event, yes, it was related to heavy rainfall, but studies show that snow and the accumulated snow prior to this event was quite influential as well, up to 50%. So that raises the question of whether or not we can only manage our system by just relying or investigating a single driver. In Toronto last year, we had a wet period and then intense rainfall. It caused damage of about $1 billion. One of the main reasons that the flash flood was exacerbated was the preceding wet period. Soil was saturated, so it immediately turned into runoff. In Texas, recently, in 2024, the heavy rainfall, due to many reasons, the thunderstorm, the residuals or remnants of the hurricane, it increased the river levels by a few meters, I think up to 7 meters in a few hours. That combined with heavy rainfall on urban lands, it caused catastrophe. So we had a combination of both pluvial and fluvial flooding. So when we look at flood events, these events are not just caused by a single driver, they are caused by multiple drivers. In inland areas, the floods are associated with heavy rainfall, but also the antecedent conditions. The soil, if the soil is saturated, it doesn't allow the water to get absorbed, and so it turns quickly into runoff. In areas in the north, especially in Canada, rain on the snow is a major event. So we have the snow on the ground, winter time, later in winter, early spring, still snow on the ground, then we have rainfall. That rainfall combined with snowmelt can lead to flooding. In coastal areas, we have another problem. It's not just the inland and heavy rainfall, river overflows that can cause flooding, but the coastal water levels, tides, storm surges, waves, seisures, these events affect those coastal areas as well. So what if these multiple drivers, they occur at the same time, simultaneously? So obviously the result will be much more impact and catastrophic flooding. Now, these might seem quite rare, but recent events, like for example, Hurricane Melissa and many other hurricane events, or the extratropical cyclones that affect the Atlantic, show that these events are not rare anymore. They are happening more and more frequently. So we took two of the components that are quite common. One is the rain on the snow. The other one is saturation excess flooding. So saturation excess flooding refers to a scenario when the soil is already saturated and then you have heavy rainfall. So we were interested to see how these events are expected to change in the future climate in North America. So these two figures show how they are spatially varying currently in North America. This is for rain on the snow. This one is for saturation excess flooding. So overall, in higher elevations, including the Great Lakes region, regions on the Pacific, we see areas that are prone to these kind of events, rain happening on snow. In the saturation excess flooding, we have regions on the east of US, some parts of the Pacific Northwest or the northeast of Canada that are susceptible to these events. So these are not rare events. They're quite probable in our region. What happens in the future? Based on these climate models, we can see that areas from the Pacific Northwest to the south, they don't show quite a bit of increase in rain on the snow. Partly because in a warmer climate, the snow tends to decline. So if you have reduced the snow, chances of having significant rain on the snow declines as well. There are some regions in the higher latitudes or higher elevations that still have snow during warmer periods, so still below freezing level. So they are susceptible to these kind of rain on the snow events. But interestingly, the types of events that affected Toronto last year, GTA area, these are expected to become much more frequent in almost all regions, from the Pacific to the Central and other regions. So that is helpful to know that in our future planning, what kind of drivers are expected to cause flooding issues. When we look at the future, one question is, there is always variability. There are the teleconnection effects, El Nino, La Nina, so there is this variability, and we are talking about climate change. How do we know that climate change is actually making a sensible change? We see just percentage changes, but are these really strong enough that show us a signal that we should expect a big change in the future? So one of the advantages of these climate models is that we can do many, many simulations just by perturbing an initial condition. When you do that, then you have a single model, but many realizations of possible future scenarios, and that's a reflection of the internal variability of whatever system you're studying. So that internal variability reflects the noise of the systems, ups and downs, and the average of the overall changes reflects the strength of the signal. So if you take the two and we divide them, that gives us a ratio, signal to noise ratio, which if it's large, it implies that the signal is strong. If it's low, it means that, well, either the signal is low or there's so much noise that you can't really differentiate the signal. So if you take that and, for example, you take rain on the snow for different warming levels, we know that as the temperature, global temperature continues to rise, then the overall rain on the snow, especially in lower latitudes, including the Great Lakes, is becoming reddish. So the signal is becoming stronger, but to the negative side. So that's an indication that rain on snow is declining due to climate change. Areas on the higher latitudes, though, show slight stronger signals towards increases. With regard to the saturation excess flooding, we see clear signals, especially on the east coast, east of US and the Pacific, that show increases in these types of events, even considering the noise of the system. So we are always interested in the risk. It's not just the hazard, but also how it impacts the societies. If you overlay those on the so-called social vulnerability index, that's an indication of the vulnerability at regional levels, that can give us an indication of the degree of risk we should anticipate. So for example, in the US, for rain on the snow, there are patches of higher risks close to the Pacific, but what we anticipate much more in terms of the risk is associated with these kind of saturation excess flooding. So the message is this. In the future, we expect to have more frequent, more intense types of flooding that was driven by heavy rainfall on saturated soil. Especially in Great Lakes, we did a case study and we found similar signal. In terms of rain on the snow, we expect reductions. In terms of increases in terms of heavy snowmelt. We also expect reduction. And in terms of saturation excess flooding, we see more or less increases in the entire region. Another interesting question for us was looking at the West Coast. On the west, on the Pacific, as you know, in the Atlantic side, we have the extratropical cyclones, hurricane types of events that cause flooding, extreme wind. On the West Coast, we have the winter storms, but also atmospheric rivers. These are like rivers in the sky, full of moisture, that when they approach the higher elevations, they dump quite a bit of rainfall. So at the lower levels, they are beneficial. They support the water storage. But at the intense levels, they can cause trouble, like what happened in 2021 in British Columbia. So these events are quite common in that region. Our question was, how common are these events combined with these types of compounds, like rain on the snow and saturation excess flooding? Interestingly, we found that most of the regions on the coast are in fact a type of a compound inland flood associated with atmospheric rivers. So when there is a heavy rainfall due to these kind of ARs, they usually combine with either snowmelt or preceding rain conditions. What do we expect in the future? We expect some increases in these types of associations between them. Okay. Now, in terms of, now let's move to the coastal environments. As you know, Canada has the longest coastline globally. So coastal environments are susceptible, of course, to sea level rise. They are susceptible to tides, storm surges, and waves as well. Storm surges, waves are generated because of extreme winds and low atmospheric pressure. Good example of these are hurricanes. During a hurricane, there is a very low atmospheric pressure, extreme wind, so they generate storm surges and waves. They also cause very intense rainfall. Two recent examples are, the one is the Hurricane Melissa that impacted Jamaica and then Cuba. It was called the hurricane of the century. The intensity of wind was so high that they compared it to the Category 4 tornado, but in a much larger scale. Very devastating. The other one is the Typhoon Kalamagi that affected the Philippines, and there were some demonstrations afterwards as well, partly attributed to the flooding and the way it was managed. So in coastal environments, we are dealing with other drivers that cause problems. Of course, we have the sea level rise, but we have the wave effects and storm surges. When storm surges occur on top of the tides, they can exacerbate the flooding in coastal environment. Now, traditionally, we study these events in isolation, but now we know that these are interrelated with what happens on the land as well. As I said, during a hurricane, for example, there is heavy rainfall and there's a storm surge. So we need to consider all of those effects. So these are the so-called compound coastal flooding. We have multiple drivers, both in the ocean side, but also on the land side. Now, if we study these events in isolation, the risk is that we will miss the combined risk and we will under-design our infrastructure. So statistically, we know that every driver has a distribution, and if you plot that in a bivariate figure, then we might see some relationship between them, meaning that if one is showing increase, the other one is showing increase as well. So there is some positive interrelationship between them. What does it mean? It means that there is a chance when, for example, a storm surge happens and subsequently we have an intense rainfall as well. But the point is, in a changing climate, Yes, the individual drivers might increase. We might experience more intense precipitation or higher storm surges. But the interdependencies between them is as important. In this case, you see that if only the interdependency between the drivers increases, then that can increase the risk of the hazard itself. So in compound coastal flood analysis, in fact, we consider the interdependencies between the drivers and quantify that to assess the probability of such hazards in our coastal regions. So we use extreme value theory, we use the copula functions, etc. These statistical methods to have some probabilistic sense of these extremes in our coastal environments. So the data is there. Historically, we have tidal gauges, hydrometric gauges, and weather stations that we can use to assess these kind of events in a historical sense and assess, for example, if there is positive or negative correlation between them as a first step, and then study their variation and distributions. But there's always a question of what should we expect in a future climate when either the storm surge might change and the precipitation might change. So we took the numerical model simulations from the Telemac to support the simulation of storm surge and waves for a Pacific coastal study. It was driven with Cortex RCMs, and we used the same models to project the precipitation in the region. And we came up with figures like this. This is for Tofino, our specific case study. And we know that there is some positive relationship between precipitation and storm surge in Tofino. So that means that there is risk of compound flooding in Tofino. And now our interest is on these extremes, both in terms of precipitation and storm surge, as well as their interrelationship and dependencies between them. After realizing this, then we are interested in their changes in a future climate, whether or not each one of these intensify going from historical period to the future period, or whether or not their dependencies change in a future period. And either of these changes will be reflected in our design factors. Now, we are not just using the individual return levels for individual drivers. Now we look at the joint return levels, the probability of the joint occurrence of multiple drivers. So what we found was that, and many studies have shown that as well, just by considering the dependencies, the interrelationships between the drivers, you will see that the risk of these events drastically increase compared to when you assume they are independent. So that's one message. The other message is that as we move to a future climate, there are regions that show the joint return periods drop, meaning that these kind of joint occurrences become more and more intensified and frequent. What is the usage of these? After doing all of these climate modeling, then we can use our numerical model simulations and watershed models to assess the impacts of either of these compound floods on the system, and then do risk assessment and develop mitigation measures according to that. This is a case study in the Caribbean, the St. Lucia Island. An interesting case study because the island is affected by the ocean and the coastal water levels, but also this river, this is called the Latornia River. As you see, it comes from the north. There is a sharp bend just before it gets to the Hewanara International Airport, and then another sharp bend, not a very good scenario, especially when you have extreme flows. So usually this dike breaks and it causes flooding in the airport's runway. So they were commonly affected by hurricanes, including Hurricane Matthew, and the failure of this infrastructure led to the failure of many things, including their tourism activity and their economic and export growth. So we simulated this hurricane effect on the island, considering both coastal water levels and rainfall. This is an aerial image that shows the area after flooding, a lot of erosion. And we set up the model for that case. And then ultimately, we had a probabilistic model to show which areas are affected by flooding. But that wasn't it. The problem was we have multiple infrastructure. We have multiple systems that are interconnected. Failure of one can affect the failure of the rest of them. So we have a complex system in which different components are connected to each other. The tourism is connected to the airport, for example. So we had to come up with approaches to make these connections. So we worked with a company called RiskLogic. They had done extensive surveys in the area, and they found a connection between the entities. We had close to 200 entities, and with the connections identified. So the objective was to set up a model, and the objective was to be able to simulate the overall risk to the system, not just the risk to individual entities. So we use a approach called strongest path method. We combined it with Bayesian network to have a probabilistic model. So essentially, each one of these nodes represent an entity, an infrastructure entity, and is connected to the other one. Each node, each link has a strength that shows if the dependency is strong or not. With a hazard, this hazard can lead to the failure of one, and the system models how that failure propagates into the system, which ones are more susceptible. So what is the overall impact of the failure of one node on the whole system? So that helps us identify vulnerable areas to perhaps build redundancy and increase the resilience. But in our infrastructure, usually what happens is that the system is not static. It fails due to a hazard or other problems. And then after some time, we have the restoration. Maybe it goes to the original service level or somewhere below, or maybe it never recovers. So it's important to be able to model this behavior. So we extended this system to a dynamic system. Now the states of the next time interval is connected to the state in the previous time. So that allows us to model how the system reacts through time. And ultimately, we get to a point where we have graphs like this that show how each one of these individual infrastructure systems respond to the failure, and after restoration, how they recover. For example, if the tourism fails because of the airport failure, then after the airport is in the recovery mode, the tourism will recover with a time lag. The system is not perfect. There's a lot of subjectivity in it because we have to determine what is the recovery rate. It requires lots of data, but that gives us a good understanding of how the system would behave. Okay, so that's my talk. I hope that I've made the case that many of the extreme events are interrelated. They don't occur in isolation. And when a system, an infrastructure system fails, that failure can propagate and increase the risk of the overall failure of the entire system. So in our risk management, risk planning, we need to consider these multiple drivers and their interactions, as well as the entities of the infrastructure and their interconnectedness. And with that, I end the talk. Thank you very much for listening. Ready for questions.
Oh, hi. I'm Poonam from, well, I just retired from System Design Engineering. I just have a few questions more on the technical side. I really like your talk, and it's a very comprehensive evaluation. I think what you're doing the right thing to do, and it's not very commonly done. Because I'm coming from systems background, I really love it. I like both your studies on cupolas as well as on basin networks. Both we have also done before, so I just have a curiosity question, I would say. I think it was slide 33 and 34. Can we see it? 33 first. One before. Yeah, I mean, this is a very nice one where I'm just looking at the left side, the graph. At least my understanding from what we have done is this is not a normal cupola from looking at it. But I go to the next slide. Can I see, I don't know, the one at the bottom left looks like a normal cupola, maybe not. On the top right is not. So I'm wondering, can you explain a little bit about the technical part of this?
Yeah, sure. First off, this is a schematic. This is not the actual copula. And both of those are just for the presentation. So what copula does, so essentially, as you know well, but for the audience, if you're studying one driver to evaluate it probabilistically, everything is random, so we have to have a probabilistic framework. We use distributions, right? With the distributions, then we can look at the tails of the distributions and find the exceedance probabilities, so chances of the exceeding that intense event, and translate it into return period and return levels. But when we are dealing with two or more drivers, now this probability becomes a joint probability, so we are in the higher dimensions. Now, if you map it on this surface, then it looks something like this, right? So to make this connection between these joint probabilities, we have a problem, because most of the statistical techniques, they assume this normality assumptions. You know, if both distributions are normal, that's easy, but many cases, especially with extremes, the distributions are not normal. Pearson, log normal. So connecting those is problematic. Copulas are quite commonly used to make this connection. Now we use the Archimedean copulas because they are more suited functions to capture the extremes, because we are mostly interested in those specific extreme events. But there are like many tens of copula functions that are available that they serve different purposes. So what copula does, it basically essentially first transforms it into a probability space from 0 to 1, and then they create a joint function. I don't know if it addressed your question, but we use the Archimedean copulas mainly for this kind of extreme analysis.
By variable? Is it by variant? You didn't go beyond by variant?
Oh, we did, yes. We did the trivariate as well. Yes, the trivariate, we use the so-called Wien copula. So that Wien copula allows us to do the conditional, two events condition on a third event, or so on and so forth. So that gives us a lot of flexibility. So with the trivariate copula now, we have three drivers. We have the extreme water levels, we have extreme precipitation, and also extreme flows. So we can assess their codependencies as well.
Thank you. We've got another question here.
Good morning. Thank you so much for the presentation. It was very interesting. I would like to ask you, I see the innovation about the compound hazard and how this approach can estimate the interruption between different events, but I would like to know, in your opinion, how far the water industry of the companies, of the consultant, and to taking this approach, like take the interruption. I mean, my question is, these steps of research are more now in developing, or we are so far to implement this in our water industry?
Yeah, this is a very good question. Thank you very much. So what do we use for our urban flood modeling? We use IDF curves, intensity, duration, frequency curves. Very traditional. And as the name implies, it's the intensity of rainfall. Okay? It doesn't account for snow. It doesn't account for antecedent conditions. It doesn't account for anything. So at this point of time, what we notice is that many of these companies and industries, they are more interested in updating the IDF curves to have, a better understanding of how precipitation will change in the future. So that's the level they're interested in. In terms of flood mapping, if you look at the flood maps of conservation authorities, we have 36 conservation authorities in Ontario. They're all riverine flood maps, all river flood maps. What about pluvial floods? What about groundwater floods? What about their interactions? Nothing. So yes, some insurance companies, they develop pluvial flood maps as well. I know this is hard, but this is a factual case. This is lacking as well. Compound coastal flooding, especially in the US, because they experience lots of these hurricanes, so for example, in ASC, I'm part of the committee to develop guidelines for compound coastal floods. And there are lots of research being done. In Canada, still not. So we are mostly at the research side. The research shows these events are very interrelated. Maybe at the policy level as well. In BC, for example, there was a big report they put together. Part of it was the multi-hazard site. So we talked about how wildfires can intensify, or the floods after wildfires, and what all the debris flows, et cetera, can be problematic. So people start talking about that. But as I said, even the term compound is sometimes used interchangeably with concurrent or with other terms, or hydroclimatic whiplash with swings or other. Even the terminology is not fixed yet. But the problem is that these events are growing fast, and we have to bring them sooner than later in the modeling and in our designs before it's too late. And I think it's already too late.
Thank you. One more.
Thank you so much for your presentation. My question is kind of the same, but I'm asking for more guidance. As a person who is interested in research in risk assessment and stress testing of especially water infrastructure, I understand that the traditional method in literature that they are assessing the risk and the probability of failure due to an extreme event, we can now understand that it is much higher than our estimation because of these cascading effects that leading to each other. So what do you suggest for the next step to implement these cascading events into our analysis? Is it just coupling and implementing them in a model, a hydrologic model is enough? Or I wanted to know your expert suggestion in that. Thank you.
Yeah, thank you very much.
Sorry, I'm Aussie.
Thank you. Yeah, as you said, let's take a conservation authority. For example, if they do risk assessment, if they do it, they take buildings and they take the first floor heights and they compare the first floor height to the depth of the flood. And if it goes beyond that, then it will get flooded, and then they use the depth damage curves. I think this has been there for tens of years now. Especially with infrastructure, we already know that something fails and it propagates in the system. The problem here is not the methodology. I think the methodology is the part that we're good at. The problem is with data. That's a problem we face, because now you need to access data for critical infrastructure. Accessing these are not usually public data. And even if you get access to them, you might not be able to publish the entire data. So I think this requires some momentum from top to bottom to allow people to have access to these data sets, to be able to develop these models. Because you can do research when you have access to data. And when research is published and you have a consensus of research, then it raises the alarm and people start talking about that, right? But when you don't have data and don't have that many research works, then, or many things are hypothetical, then it really doesn't resonate. So I think that's a part that needs to be done. And also in our risk assessment, many of our risk works, majority even at research part, is done at the individual entities. Very conventional, useful, but I think we should go beyond that and at least bring this discussion in our discussion part of the paper. Yeah.
Okay, one last question here from Ponu.
Sorry, I mean, again, like, pretty happy with the Bayesian networks. That's, in my opinion, it's probably the only way you can do really large, complex systems reliability analysis. So I was wondering, the one thing I would like to know is people always want to ask, what they know is just detailed simulation of everything, you know, and they want to know how Bayesian network probability will compare with this detailed simulation of the system. Have we done something like that here?
So you mean?
I mean, for example, if I'm doing dam complexity, dam break complexity, I can just do a complete Monte Carlo simulation of hundreds of thousands of years of all kind of stuff and see what the probability of failure is. But I can do that using Bayesian networks. And I mean, I would like to know that both are same, or at least nearly the same, and whether we can do the same thing here or done something.
Yeah, that's a good point. If I understand your question, that's a very long and historical problem in because my field is hydrology, right? So quantifying uncertainty is always a big interest among hydrologists. And so there are these groups that they do these Monte Carlo simulations, samplings, that they generate millions of simulations to characterize the uncertainty. There's this other group that they use a more formal Bayesian type of approaches, and sometimes there are papers that question each other. But these are all, as we know, complementary to each other. To me, I think generating these Monte Carlo-based scenarios, the SPM approach allows you to do that. So we can tweak the parameters and repeat and see how sensitive the system is for changes in the dependencies or changes in the failure risk at individual levels. I think that's quite useful. And as you said, Bayesian network is quite powerful as well. I haven't seen a comparative study. That should be quite interesting. But many of the studies we know was more of the application of these methods in the resilience assessment. Yeah, but that's a good idea to investigate. Thank you.
Thank you so much. Let's give Dr. Najafi another round of applause. Thank you so much for your presentation and for answering all the questions.